All right, this is going to be another application of trigonometry. And one of the applications we've already kind of looked at, we've always kind of known, is right triangle trig. But this is actually what's called sinusoidal motion, or we see that word sine in there. Basically sines and cosines. What about motion that deals with circular patterns? Again, implying that a sine or a cosine might be a great way to model the path, right? Well, a lot of times we think about the way around the circle, right? We do that around the circle, unit circle stuff, right? Where we can set up angles and draw them out. But again, as we travel around that circle, very simply, right? Remember that we've also talked about functions or motion. The height, right, around the circle, we can deal with going up and down, and as we go around the circle, it just keeps repeating itself, right, in the pattern. So again, the main idea of sinusoidal motion is basically to model that idea, right? What we can model with a periodic, right, function here as we go along. So give me 1 second here. Let's get rid of all that. Get ourselves a little bit of room to work with. So let's read through what we know. Sage took a ride on the Lazy Susan. It's a Ferris wheel at a local carnival. The wheel is going to have a diameter of 30 feet and turns a full revolution every 90 seconds with its lowest point 15 feet above the ground. So basically we've got a circle, right? We've got a Ferris wheel here. It's going to be right above the ground here, right? So it's going to have a diameter of 30 feet. So let's go ahead and say we've got a radius, therefore, of 15. But again, a full diameter of 30 here. It's going to complete one full revolution every 90 seconds, right? A revolution per 90 seconds. So one revolution, let's note that, per 90 seconds. I'm guessing that's going to come into play. And it's 15 feet above the ground at its lowest point. Again, the bottoming out point here basically telling us that this is going to be 15 feet right there. Assume that Sage's height h above the ground is the sinusoidal function of time t in seconds, right? Where t equals 0 represents the lowest point on the wheel. Write an equation for h using a cosine function. Now, I like that they said cosine because if we're going to be talking about the lowest point, remember that cosines are easy to graph starting from either a minimum or a maximum. So if we're going to start at the minimum, right, the lowest possible point, right, as we travel around this wheel, it's nice that we're working with a cosine. Right? Now, the height at any given moment in time is going to be h, or basically we want to set up h of t, right? We want to plug in the number of seconds, find the height. Okay? Well, in order to do that, we need 4 basic things. Right? If we're familiar with our sinusoidal graphs here, sines and cosines, typically we've dealt with these in 4 different letters. We've got d being the equilibrium level, right, or height. And we can do plus or minus. Again, we'll pick one of those. The a value, again, which is going to deal with our amplitude, or sort of our half the total height. We're going to deal with a cosine this time, but we could easily have said sine. Right? Inside of our function, we're going to set this up, again, as b, which deals with the period of our function, and times, we'll say t, normally we would have said x, minus c, right? That's that phase shift idea, whether or not we need to shift left and right. Now, the nice part is, right off the bat, if we start to try to define a, b, c, and d, right, I'm immediately going to say, well, hey, if we're dealing with a cosine, and we're going to start at the minimum point on my graph, right? When we go back to that sort of function idea, that means we're already dealing with the fact that we're at the bottom of this curve. We're going to go up, we're going to max out, right? We're going to come back down, and we're going to minimize. Again, when we continue that curve, those bottom points, right? Well, that first one's going to be right on the axis. We're going to say we're starting at the lowest point, which means that c can be equal to 0. We're not going to be shifting left or right at all, right? We're going to start directly at 0 there. Now, another thing that we can find fairly simply, again, if we're going to draw that curve, I'd like to know where the middle is. Well, the middle of our wheel, right, would be halfway up here, right, where that radius is, or right where that, center of the circle is. Okay, we're 15 feet up, and then we have a 15-foot radius. So this distance is also 30. I would say that our middle line, our equilibrium, is going to be at y equals 30, or h equals 30 here on our graph. The amplitude then would be the distance again up or down from that equilibrium. Well, aren't we exactly 15 feet up and 15 feet down from the middle to get to our highs and lows? So again, I would say that A is going to be 15. However, because we're going to start at a minimum, I also want to make sure we use a negative 15. We want to make sure that we're starting again at the bottom of this cosine curve over here, not at the top. And then finally, we just need the B value, right? Well, remember B basically deals with the period, right? And we know that we complete, if our input variable is in seconds, we complete 1 revolution every 90 seconds. So this, essentially, right, is going to be our period. We're doing 1 revolution every 90 seconds. Okay? 1 revolution every 90 seconds. Which means if we do a little converting, again, that's 2 pi radians every 90 seconds, or basically pi over 45, right? Would be radians per second, right? Radians per second. Well, we know that it takes, again, 90 seconds to complete 1 revolution. So our distance along the x-axis there is 90, right? Which very simply means, again, we take that x value, remember that the period, right, equals 2 pi over b, or if we do a little converting here, right, multiply by b and divide away, then b equals 2 pi over the period. Well, that's essentially what we found over here, right? 90 seconds was the period, 2 pi over 90, which just means, right, very simply, this is my b value. Pi over 45 essentially should be our b value, right? 2 pi over b, 2 pi over every 90 seconds will achieve us that number. And now we can write our function, h of t would be equal to then, well, we're going to be 30 feet high to start with, or range around, right? That's basically our height of the middle of our circle. We're going to say minus 15 because we're going to start at a minimum 15 feet below that. For a cosine value of pi over 45 times t. And again, minus c, we put minus 0. So again, this goes back to that definition of sines and cosines, that way to graph them as periodic functions, but sometimes helpful to think about them again in that circular motion fashion, right? We would start by going up fairly slowly, and then we're going to rise quickly on the side, and then top out, right? Just like we're topping out on our curve at the top here, and then we work our way back down, right? But again, if we're going to start at a minimum or a max, a cosine is nice. If we would have been starting in the middle, a sine value wouldn't have been a bad idea. Or you could do a sine value, but you'd have to back up a quarter circle. We would have had to shift, right? Then we would have created that c value. We would have had to shift over a little bit. If you have any questions about sinusoidal motion, make sure you talk to your teacher. Otherwise, have a great day.